Welcome to Lecture 3.2, Visualizations in MATLAB for Introduction to Programming in Mechanical Engineering. By the end of this lecture video, you will have an understanding of the importance of storytelling, how to use compelling visual aids, and how to write a custom visualization function for the vector cross product. This slide, the table of contents, contains hyperlinks to each of the sections to make the downloaded PDF easy to navigate. Mechanical engineering problems are usually highly relevant in the real world, and therefore they often have relatively obvious ways to find intuitive and useful ways to visualize information. The goal of this lecture is to convey that code by itself is not sufficient. It is vital to learn how to tell a story through the code. Take this example of a bridge under load. Each member of this truss is colored according to how much load it carries. Or consider this example of the same truss under load. Now the visualizations showcase how it deforms. In both of these examples, the subject is the same K-truss under load, but both images clearly communicate completely different information. Consider how many words or numbers would be required to convey the same information. Half of our job as engineers is to communicate our work. As much as some of us would sometimes prefer to work solo, we do work with other people and often in service of a broader goal. Therefore, we need to learn how to tell stories about our work. Being able to create compelling visual aids is a powerful skill that can go a long way towards effective communication. In the previous lecture, we wrote a custom cross-product function that takes two 1x3 vectors as input. Given that it is difficult to visualize three-dimensional vectors in our heads, let's write a named function that plots all three of the vectors. We'll construct it in stages, starting first with an outline. The function's input will be two 1x3 vectors, just like the cross-product function from the previous lecture. The purpose is to visualize the two input vectors and the output vector to gain a better sense of the cross product. And the output is just a 3D graph that shows all the vectors labeled with a legend. Creating an outline right now will help us write code later to give us some structure. So let's start with the skeleton of the function, again using the function and end keywords as we discussed before. Then there will be two vector inputs, v1 and v2, and the output will just be a figure, so there are no variables that need to be passed back from the function, therefore the brackets are left empty. Step 1 is to evaluate the cross product between v1 and v2. Step 2 and 3 are to plot the first and second input vectors, and step 4 is to plot the cross product vector. And then finally, step 5 is to apply formatting commands to make the output more visually comprehensible. To fill in step 1, we'll just use the custom function written in the previous lecture and store the output in the variable c. For steps 2 through 4, we'll use the quiver3 command. It takes 6 inputs, which are as follows. First, the x start input, then y start and z start, followed by the x length, y length, and z length. Together, these 6 inputs define the 3 coordinates at which the arrow should start and then how long the arrow is in each direction. For simplicity, we'll consider just 0, 0, 0, or the origin, as the start point for the vector, which means that we can plot the first input vector v1 as follows. Quiver3, 0, 0, 0, and then v1, 1, v1, 2, and v1, 3. To plot all three of the vectors, we have to first create a figure object. Then we apply the hold on command, which enables the figure to retain its contents with each new plotting command. Without this command, each subsequent quiver3 command will overwrite the entire figure. Then we follow the format mentioned earlier to plot v1, v2, and c, the cross product vector. Right now, the output graph is not very pretty. That's where formatting commands come into play. Here are the things that we'll change in order to make it more presentable. First, we'll color each of the vectors. Then we'll make the arrows thicker. We'll view the entire plot in 3 dimensions. We'll implement a uniform aspect ratio for each axis, change the axis markers, increase the font size to make it more readable, add a legend to label the vectors, and we'll add box and grid lines, and finally we'll add some axis labels. MATLAB allows color codes to be added to the Quiver 3 command. This hyperlink on the page directs to the MathWorks documentation on the various options. We'll cover V1 in blue using the B in quotes. Then we'll cover V2 in green using the G in quotes. And then C will be colored red using the R in quotes. Again, with the Quiver 3 command, we can also add a name value pair using the line width argument to increase the thickness of each vector. We add the string line width with a numeric value in the following argument. In this case, we'll use 2. As an aside, name value pairs like this are very common in MATLAB, especially in plotting commands. Now, adding the view3 command here displays the graph in 3 dimensions. We add that line at the end of the code shown before. Note that from this point forwards, some commands will be hidden to save space. They are labeled with a comment. After coloring each vector, increasing their thickness, and viewing in 3 dimensions, the output now looks like this. The daspect command takes a 1x3 array as inputs, and it is used to specify aspect ratios for each of the axes. For our purposes, we want a uniform aspect ratio, so let's use 111 at the end of the existing commands inside of daspect. The output now looks like this. Now the commands xticks, yticks, and zticks allow you to specify markers on each of the axes. For this demo, I only want there to be markers at 0 and 1 on each axis, so the xticks, yticks, and zticks command reflect that. The vectors that you put into these commands can be of any length. I am just using 0 and 1. Now with these markers added, the output now looks like this. Now the command setGCA adjusts various properties of the current axes, and it allows you to specify certain properties within the command. We will use this command to adjust the font size to 16 point for the entire figure using, again, a name value pair. Now the numbers labeling each axis are much larger than they were before. Now the legend command is used to add labels to the contents of the graph. It takes a series of strings corresponding to the order in which the content was added to the figure. We added V1 first, so that will go in the first argument. Then we added V2, and finally, then we added the cross product vector V1 cross V2. With a legend, there is now a box that contains labels for every vector in the graph. Now the box and grid commands refer to the box and grid lines respectively. Box on specifies that the outline of the entire plot box should be shown, and grid on specifies that grid lines at the axis markers should be enabled. The plot now looks like this. The commands xlabel, ylabel, and zlabel add labels to the corresponding axes. We'll set the xlabel as just x, ylabel y, and zlabel as z. Now the plot orientation itself is much clearer with our plot box shown here. This slide here contains the entire function written out for your reference in the downloaded PDF. Keep in mind that it is split in half in order to fit on the page, but these two halves should be one block of code. We can now test this function by visualizing the cross product between the unit direction vectors I hat and j hat, which we know produces the third k hat. Then we can test j hat cross k hat, which produces I hat. Note that the colors have changed correspondingly. And then k hat cross I hat, which produces the j hat vector. And for fun, let's show what this looks like with just 2 random vectors. This can be a very helpful tool for visualizing cross products for yourself. In summary, as mechanical engineers, we solve problems for a reason. It is necessary to effectively communicate what we have done. If done well, visual outputs from programs can be extremely valuable in conveying the program's results. By using the quiver3 command here and many formatting specifications like line width, xticks, and legend, and a bunch more, we plotted all three of the vectors in the cross product in a visually clear way.